tenemos una escuela por la que están pasando continuamente los arquitectos más importantes del mundo. Estamos muy orgullosos de ello, pero también estamos muy orgullosos, o especialmente orgullosos del acto de hoy y tener a alguien que es completamente inspirador y alguien que ha sido tan generoso como para hacer un acuerdo con la Escuela de Arquitectura para que también poder recibir a nuestros estudiantes dentro de su firma. Para mí Skidmore, Owings y Merrill desde mi infancia, y digo mi infancia porque me aprendí el trabajo de ellos por primera vez en muchos meses en Estados Unidos en el año 74, mientras conseguíamos que Nixon dimitiera, y me enamoré completamente del trabajo de Son, especialmente de Gordon Bunshaft, que lo convertí en uno de mis ídolos toda la vida. He ido siguiendo todo el devenir de la arquitectura americana en muy gran medida a través de lo que ellos hacen. Y en esta parte de la escuela, que es no solamente el diseño y la creatividad, sino la creatividad aplicada al cálculo de las estructuras y el entender cómo las estructuras generan los edificios y muy especialmente los edificios en altura, para nosotros es muy importante este acto y es muy importante este momento. Mark, thank you very much for being here, being with us, for your friendship and generosity, and for being already a part of the ETSAM. You are not made. You are not made in ETSAM.
No, thank you.
You are not made in ETSAM, but don't worry. When you will keep on coming here,
Yeah.
we'll make you made in ETSAM.
Okay.
Thank you very much for being here with us.
Thank you. So hello everyone and welcome to the students from Alcalá that are here as well. And Rosa, thank you very much for organizing that and having the students here, along with some great students that we met yesterday. Here we're going to talk a little bit about the work that we did yesterday in the studio. And what I thought we should do perhaps is have two parts to this discussion. And it's a journey through design from the perspective of a structural engineer. And in particular, it's design of tall buildings. And our firm, SOM, is a design firm that has been in existence for a long time. It was founded in 1936. And the good news, really, is that we have survived that long as a design practice. The bad news and the challenge is that you have to constantly reconsider what you contribute to the design community in the world, right? So you're challenged by trying to come up with new ideas. And so our goal, our mission is take the fundamentals of design and try to come up with ideas that might change the way we practice. So what I'm going to step through for you today is a series of chapters, so to speak, of a book that I was part of writing a few years ago. And it starts with perspective or history, and it ends with the environment. And it's a step-by-step process, we think, in design. And this book is about engineering, but it's about how engineering, structural engineering, relates hopefully to architecture, hopefully good architecture. So a few years ago at Stanford University, we had the opportunity to teach a studio class similar to what we have done here yesterday, starting and then finishing today. And as part of that, there were a series of notes that we created for the lectures. The lectures became this book. So Rutledge approached us about it, and we published this. In fact, it's in the second edition. It's not a very expensive book, by the way. I'm not here to sell it, but on Amazon you could buy this book for, I don't know, $40 or something, US dollars. It's not very expensive. But what it tries to do is look at architecture through the lens of a structural engineer. And And so we believe it starts with some level of perspective on design. And if you look at cities and the impact of the tall building, it makes a difference. So these are iconic moves that change cities. In this case, the Sears Tower at the time that it was originally built. And you can see that there's very little around it. But if we step back for just a minute and we look at history, and we're forced with difficult situations, the Chicago fire of 1871 was a good example where there was an abrupt change in the way we use materials. We started to use cast iron in taller structures. We tested the limits of other materials like masonry in tall buildings. This building still exists in Chicago. It's the tallest masonry building in the world, the Monadnock building. Unfortunately, the home insurance building does not exist anymore. The Reliance building exists, and it's one of the first examples of a steel frame that was clad for a number of reasons: safety, controlling temperature, and protecting the steel frame. This is a hotel that you can stay at in Chicago if you visit the city today. In the mid to late 20s, these three buildings emerged in terms of design. The first one, the Empire State Building, was the tallest building in the world for a long period of time. They used fundamental technologies to actually design and build them. They were all structures of steel. So I like to think of the ages of the skyscrapers as 5 ages. 5. The first, starting with the use of material, cast iron or steel, that was done in the late 1800s. The second was this sort of brave idea of using steel at very great heights, with the 3 buildings shown here: the Empire State Building, the RCA Building, and the Chrysler Building, all of which still exist today. So in the early 1930s, these aren't structural engineers, by the way. These are architects. Okay, so some of the buildings you recognize. This is Philip Johnson, who just recently passed away. But I show this because it's about a personal approach to design, right? So architecture is in taller buildings is a bold move. The engineering that is behind a lot of these buildings is quiet, but still super important. After the war, and when materials were very scarce, we had different minimal buildings that were built in New York City on the right, Chicago on the left, where we used these ideas, and these are both SOM buildings, where we used minimal uses of material, exterior wall systems that were quite thoughtful and quick to build. So our firm was founded by these 3 men, Louis Skidmore, Nat Owings, and the structural engineer actually that came to the firm in 1938. 2 years later, he was a man that was probably brought the sort of calm, rational approach. He was both an architect and an engineer, John Merrill, and his son later was involved with the firm after his death. As it turns out, Nat Owings met Louis Skidmore through his sister. He dated his sister. It was very controversial. They eventually married, but Louis Skidmore didn't particularly like Nat Owings in the beginning, and it was a relationship between architect that was, we'll call him the pure designer, and Nat Owings, who was also an architect, but somebody that was very interested in policy and major plans and relationships with clients. In 1982, Fazler Khan, who's a structural engineer with with SOM, a very famous one in terms of developing systems, wrote this piece that was never delivered. He died before it was actually, this address was ever given. But in the piece, part of it said, today it seems that the pendulum has swung back again towards architecture that is unrelated to technology, and it does not consciously represent the logic of structure. In many cases, facade making has become a predominant occupation. Postmodernism was a movement in the United States and other places around the world where structure was one that was not celebrated, but the idea of excess material perhaps was. And when I started at SOM, this was one of my first projects. It's the NBC building in Chicago, a good building. Good building, it's still there, it's still very functional, it's still fully occupied, but it was one that represented postmodernism. So the question was, in this fourth stage of skyscrapers, how would it relate to the future, and how would it influence the work that I perhaps would be involved with? When you look back on important moments in history, Myron Goldsmith, as both an engineer and architect, created moves that went on to become systems that were built, systems that we still wonder about in tall buildings. In this case, the mega frame that was infilled with a more lightweight frame as part of his thesis. The braced frame that expressed demand in the structure and the density of material as it got toward as the building approached the base of the building to resist lateral loads was part of this concept. This sort of clear idea of hierarchy of structural systems was one that he developed in his thesis work. And the two ends of the building, two different opportunities of bracing the structure, both valid, but using slightly different ideas. So it was the engineer, Kahn and Graham, that worked together, and that's what we stress in the coursework here and other universities around the world. How does the engineer and the architect relate to one another and create moves that change the way we see architecture and the way we use material? So the Hancock building emerged in the late 60s as one that started with two buildings, two 40-story buildings that became 80 stories. And the argument was that the material that could be used in this tall building would be similar to the 40-story building if it was placed properly. So this braced tubular frame was conceived. The expression of structure is within it. The idea of load sharing within the structure was all part of the concept, both to resist wind and gravity loads within the building. But it was these moves, in particular the Hancock building, which was built before the Sears Tower, that helped shape Chicago and create density and create, we'll say, a spark or an impetus for future development around these taller structures. The fundamentals of the tall building and design, and if you were to look at wind engineering and form, this is one of the most optimal shapes that you can conceive in a tall building. It's beautiful, but probably not so practical. But we start here and think about, well, what the future might bring in tall building design if we had forms like this. But we reflect back on the simplicity and clarity and sustainability that we perhaps can use in more simple buildings, maybe even at scales that could vary from modest to fairly tall. So the idea of the moment frame and the expression of the frame with, in this case, the exterior wall set back, so the frame is red. The idea of clarity at the base of the building. We still wonder about how we approach our buildings and how we use them at the entryway. So the clarity of structure as it meets the ground and how we enter. This has been a challenge for many tall buildings around the world in terms of how one interacts with the building itself. So for instance, the Sears Tower and the Hancock building in Chicago have gone through many changes at the bottom of the building. In fact, today it's still happening at the Sears Tower, right? So how do we interact with the structure at the street. We wonder about systems that we've developed from the past. So for example, the frame, or maybe in a more sort of progressive way, the tubular frame, where the length of the beams are similar to the length of the columns, to the brace system like the Hancock Building in Chicago, where it's concentric, efficient, but maybe not the most efficient. So we're finding that frames that look like the one on the right are even more efficient. And if you look carefully at it, you'll see that the frame itself is asymmetrical. The frame is nominally a 3/4 to 1/4 geometry on the elevation. But what you'll also see is an interpretation of it. And I'm going to talk a little bit about this later, that you don't necessarily have the perfect structural engineering answer to the problem. We need to consider it from a subjective point of view in terms of the architecture and use. You can take building forms that are efficient, that have, in this case, a Y-shaped plan, and you could think about it first like the frame that I showed you before. Secondly, perhaps like a braced system that is more regular throughout the height. Or you can use the noses of the structure for large structural elements that you would lock into the core that you can't see. So these are options, ideas, same geometry, but different systems, and all of them efficient. When we start out with the fundamentals of design early on, it's something that we in our studio look at for clarity relative to use. So we've got a residential tower and an office tower and a podium that all have different uses and different structures. And to read it gives you an idea of what perhaps is within. And we create these with freehand drawings. Even in the digital age, we think that this idea of tangibility of ideas relative to your hand and your eyes is something that brings these forward. So the concrete building on the left for the residential tower, the steel braced frame for the office building on the right. And in fact, the idea is to use composite materials for that building, where the horizontal systems are concrete and the vertical systems are steel to resist the lateral loads. So from the fundamentals, we move to the site, and we don't know a whole lot about sites except the environmental conditions, the geotechnical conditions, the lateral loads that might be there from wind and seismic. This is the foundation of the Burj Khalifa. And you can see the scale difference between the footprint of the tower and the trucks that are there on the ground. We used a deep foundation with piles that was capped with a raft to create that structure. But winds that impact buildings and create vortices are those that we use in design. And the idea of movements of buildings is not what you expect. So for a tall building with winds that might be approaching the building this way, the movement's actually left to right, because the vortices that enter around those buildings tugs on the building from left to right, and that's where the dominant motion comes from. We worry about winds at the ground and how people interact with these towers. And we think about code applied winds and then winds that we might see in the wind tunnel. This is a tall building in Moscow that was never built. It had a system similar to the Hancock Building. But in very simple terms, we have wind that's applied on the windward side and the leeward side. And we take those pressures and we apply them over the height of the building. And the reason for the increased size of the arrows is not because the pressure increases violently over the top, but what it does is it's trying to model the tributary area that the wind impacts. So this is a force based on the amount of pressure that building is seeing and the amount of tributary area that we're trying to collect and apply to the base building. So for instance, this large arrow here is trying to account for the top of the building to apply a single point load at the roof level, or where let's say the top of the last occupied floor. In tall buildings, Usually over 40 stories or so. We are testing the building in the wind tunnel. This is the Jinmao Tower in Shanghai. And at the time that the building was conceived, these two tall buildings, which exist today and look very different than these models, were looked at in the wind tunnel because those two tall buildings excited Jinmao. So as the dominant wind came through these two tall towers, it excited Jinmao, magnified the forces of around 25 to 30%, and we designed for them. Even though those buildings weren't there, the plan was someday to do something tall, and that's what we used for the study and the final design. But things like, where is it? Where are we trying to build this? So the proximity of the tower, typically it's half a mile radius that we look at. We look at pressure along the height of the building, the pressure taps that are used to look at localized pressure. We looked at the pedestrian wind analysis, the photograph I showed you earlier. We look at something that's called force balance, and that's taking a very simple foam model and reading the forces, reading the demand at the base, and then superimposing those red values with the characteristics of the tower, the dynamic characteristics. And then finally, an aeroelastic model that can look at different degrees of freedom. For Jinmao, we looked at 3 degrees of freedom, translation in 2 direction, and torsion. Okay, seismicity. In areas around the world, seismic design is becoming an increased part of what we do in terms of tall buildings. And here's some of the things that we think about: the intensity, the ground acceleration, the spectral acceleration, and what is the value of the earthquake? Is it a design level where we're designing components and so forth, or is it the maximum considered or maximum capable earthquake where we're looking at trying to keep the building stable in a major event? If you took San Francisco and you looked at it for the Loma Prieta earthquake, which is 30 years old now, it's actually the 30th anniversary this year, and you applied the demand from that earthquake to the city, and you compared it to the 1906 earthquake, which was much more severe. So 7.1, which was recorded in Loma Prieta, versus 8.3 in 1906. And what you're seeing is the impact of damage. And this is done through a scale that's a qualitative scale called the Mercalli scale. And this is looking at what happens to the built environment. And we can think about this in our cities. This is a really important point about resiliency and what happens during a major event. It's damage, it's downtime of business, it's where people live, right? All these things are impacted. So the resiliency that we introduce into our designs is really important. It's beyond the building code, okay? It's beyond the building code. So this scale looks at motion and what happens, and you can see it, you get the dark reds, that's very violent. In some cases, you would get collapse. We also look at the magnitude of earthquakes. We measure earthquakes. We use this information to feed into our models. We're concerned about where the next big earthquake is going to happen. So here's San Francisco, and I live right around here. So I'm straddling, which is called the Hayward Fault and the San Andreas Fault. It's the Hayward Fault that people believe is going to be the next major seismic event. And Manuel, Director Manuel was just at UC Berkeley, and I know there are a number of people that have, professors here that have collaborated with UC Berkeley. It's basically right on the Hayward Fault. In fact, their stadium straddles the fault, and it's designed for it. But that's where we expect to see the next major earthquake in the Bay Area. When you talk about magnitude of an earthquake, people always wonder, well, what does it mean? What does it physically mean, right? So if we had an 8.0 earthquake, it means that the ground acceleration is about 0.5 G. And it translates into a certain level of damage that could be expected. So there's a way to take the numeric side of the earthquake and translate it into the qualitative side through these comparable metrics. When we're designing buildings, a lot of times we're using this response spectrum. This is typically from the code. And the way to think about this especially for those students, is that the fundamental period of the building is usually the period that you get the most action from, okay? And what I mean by the fundamental period, it's the period that a building takes once it's excited to go from 0 to my right, through 0 to my left, and then it comes to rest. So a taller building takes longer to go through that motion. Softer, right? So a taller building has a longer period, and what you find is the fundamental period is out on this graph. Now what does it mean? It means that the acceleration that you're designing for is less than a shorter building, okay? So you have a shorter building with a very short period, it's going to be moving probably with the ground. And again, it's going to take high demand relative to the tower that sees lower demand. So what we're trying to do is trick buildings to actually behave like this. So when you seismic isolate a building, could be a shorter building, you're trying to push the fundamental period out that way, right? So that's the way to think about it. And a lot of people think all tall buildings, it's scary to be in a tall building in an earthquake. In fact, if it's designed right, it's the best place to be because it's going to go through the motion in a slower way. Usually interstory drifts might not be as high. And it's actually, if it's done well, it's the right place, it's the right place to be. Damage is really important, okay, in buildings of all scale. But when we design our building today, based on the building codes from around the world, we design them to be life safe. The structure may not look so great afterwards, but it's designed to keep people safe. The walls are meant not to collapse on us. The ceilings are not meant to fall down on us. The structure is meant to be beaten up, let's say, but still in service. Usually it needs to be repaired. Sometimes it needs to be taken down and replaced. But what we're pushing for is how do you create buildings that are approaching operational modes after the earthquake? How do we make them more resilient? That's a problem because a lot of times in order to do that, it costs money to do it. Okay, in the Bay Area, we're susceptible not only to the earthquake, but we're susceptible to what happens with the ground. Okay, so the bay along the waterfront, today where you see these piers, was built well out into the water. And the entire area here was filled largely after the 1906 earthquake. The Transbay project, the tower that you've seen, you probably have read about it, seen it, and the Transbay terminal is here. Part of it's actually sitting with where the water was. So this is what it looked like 100 years or so ago. And here's what it looks like today. And this area here is what we call risk to liquefaction. If you have shallow foundations in this area in the red, you're likely to have the loss of the strength of the material at the surface during an earthquake because a lot of the sands are saturated. And you basically lose the strength. In fact, in 1989, Loma Prieta, we had a lot of damage to buildings along the waterfront that were down here. So the point is, for tall buildings, you need to be down on the deep sands, or you need to have pile foundations to rock in order to develop in this area. That doesn't keep people away, because we've got a lot of development that happens right here, right in this red area. This is the financial district of San Francisco. When we talk about tall buildings, there's a mix of materials that we might use to deal with foundations, from spread footings with lighter loads to mat foundations and piles with heavier loads. What you see there is an image of the Burj Khalifa. That's the foundation mat. It's 4.5 meters deep. And you can see the concentration of reinforcement that was used there. The Jinmao Tower in Shanghai was built on one of the worst sites in the world. It's 420.5 meters tall. It's an office building and a hotel. And it has 3 basements. But the issue there was that we needed to penetrate the soft upper layers. So what we did is we drove piles from the surface down around 80 meters below the surface to create a bearing situation at the base that used these open steel pipes that were driven with what we call as followers. They were pipes that we could take away for the top section, and we would leave the rest of the piles down in the bottom. Then we created a system, and we learned about this yesterday in class. You know, how do you create temporary systems throughout a site so that you can build your tower first? That's exactly what we did here. We built a reinforced concrete system that was in between the floor levels with temporary steel columns that all of it could be removed, and while we inserted the new construction in between. And that happened after the tower went forward. And what you see at the bottom here is the tops of those pipe piles that were exposed after the soil was removed. Around the perimeter of the site, I mean, it's just raw kind of ideas, right? I mean, it's just like there's nothing beautiful about this except for the science of how it's done. Bentonite's used in these trenches, whether it's in Shanghai or at Harvard University where we did a science building. They're done in segments. It's called a slurry wall, and what we do is we insert this cage that goes down. You can see the height of the wall there. And then we pump concrete into it, and it becomes the permanent cutoff wall for water entering in the site, and it provides the means of actually making the excavation. We talk about displacements of towers. It's real. It's a real challenge. At Jin Mao, the tower core is here. The podium is here. This big black line is the actual measured deflection of that tower, and it's around 70 millimeters in this diagram. In the end, it was probably a bit more, probably more like 80 or 90, and what you also see is the predictions that we made along the way. And I'm sure that you've read about towers settling. There's a tower in San Francisco that is settling more than what was expected. And the numbers are much bigger than this. But we worry more about differential settlement, tilting, than straight down settlement. This building kept settling uniformly. Other than the problems at the street level and utilities, we don't mind. Structurally, we don't mind for the tower. But if it starts to tilt, and you can see that it is a bit asymmetrical. You have less deflection, more deflection. You wish that the greatest deflection was right here in the middle and centered around the tower, but it's not so bad. It's close enough, right? It's close enough. So forces are interesting because you can't see them, right? You can't see force. I mean, we're trying to see force through mechanisms of analysis and machine learning and other kind of nuances and crazy things that will help us to see them. But for a tower like this, you can't see it. But what happens inside of it is important, right? So the way we use the building, the loads that we put on the buildings, really important. Whether they're live loads or superimposed loads, it helps us to get the weight of the building correct. It also helps that we know what our site is like. So for instance, wind pressures over the height of the building are very important. They translate into forces based on the tributary area that they impact. And these are forces that we apply to the tower itself. When we design for earthquakes, we look at the horizontal earthquake and the vertical earthquake. These are both impactful. For many sites, we use the code for vertical earthquake effects. There are calculations that you can make. But if you wanted to be more sophisticated, you would actually do a site response spectra, and you would look at, or ground motions, and you would look at vertical and horizontal motions to design your building. There are lots of ways of doing this, and the European codes are a bit different than the international codes or even the codes that we might have in cities in the United States. But the fundamental idea is you're trying to get a base shear at the bottom of your tower. And through that, there are factors that impact it. Period is one. And also a factor called R, which is a response modifier. So for buildings like frames, R is higher. If R is higher, the effective force that your building sees is lower, right? So if you had a concrete shear wall, the ductility factor would be lower, it's less ductile, the forces would be higher, than when you compare it to the steel frame. So these are tricks that you can think of in systems for structures and tall buildings that impact ultimately what the forces are and how much material you use in the building, whether it's by code or by performance-based design, which I'll talk about a little bit later. So there are other things that we think about, seismic dead load. We're not going to get all the live load at once, right? But if you have storage in your buildings and other things, you're going to have to take a fair amount of that into consideration. Mass impacts the lateral system. Keeping the mass down is very important if you can do that, because that's going to lessen the seismic demand. So ground motion and period of buildings, I mentioned to you before, these are, this is an example of a tower in motion. This is the outline of that Moscow tower that's never been built. But it gives you an idea of how the fundamental motion of this building might be subjected to ground motions. And then we take things that are, let's say, regular, like that building I showed you with the moment frame earlier, and we apply code-related demands due to seismicity. For years, it was a triangular pattern. Now it's slightly nonlinear in terms of the application of force. And the idea in the older codes was to apply a force at the top that considered higher mode effects. So buildings that vibrate at a high mode of vibration and activates mass, that was the reason for putting that force, that higher concentration of force at the top. So you take these forces that you calculated at the base of the building and you push those forces vertically and create shears within the structure, and then story shears based on the floor-to-floor heights. And you come up with loads and bending moments. These moments are used to design things like the bases of shear walls or frames. And these are things that you can do by hand to actually take something that's really complicated and create something that you can understand the fundamentals for. This is an example of a tall building in China, in Tianjin. And the reason I show this is that the use of these buildings is very important. Yesterday we talked about elevatoring in the service area. The core is largely driven by services. And it just so happens that in a lot of these tall buildings, the geometry of the enclosed area for the services, elevators, mechanical rooms, restrooms, is about what you need for the size of the structural core in the middle. And in this case, you have a frame and you have these occupied areas that are like bay windows, right? But really great office spaces because you don't have anything in the way as you look outside. So we take these loads, we apply them to buildings of different geometries, whether it's cores and occupied spaces. But we're trying to come up with a way to create a kind of an equivalent situation so that we can actually design it. Otherwise, if we're stuck in too much of the detail, we'll never get to the finish line in terms of the final design. We need to think about the exterior wall. In seismic events, heavier systems create more demand. So precast plus glass at the exterior wall is a lot heavier than metal plus glass. In a tall building, you can break it down into initially some really simple geometric ideas where you have the core taking a certain amount of gravity load and each column taking its own tributary area. And why is this important? It's because we're trying to get the gravity loads down into these columns so that we have the load that it sees. And you can see that in certain situations where you have cantilevers, that demand is going to be higher. Column sizes are likely to be higher. Then you combine all these loads, okay, to create a force that you design to. So you combine dead loads plus, it could be loads due to fluid effects or snow or wind, live loads and so forth. And these are statistical ways of using all those loads together. Earthquakes, really important. Certain key elements require overstrength. So you see this omega factor, and that is to amplify the force for elements that you just can't lose in a major event. So sometimes that value can be 2.5, 3 times as much to put extra material there to protect that particular element. But if you were to take a tall building and simply look at the statics, this is more or less what you have. If you had an applied load due to wind, let's say, then you had gravity, you have an overturning moment, and you have resisting forces. You could then take it and dissect it and create ways of using moment arms and so forth to resist those loads and come up with some initial sizing of the structure. Language. So how do we read structures? It's really important. Some are really obvious, like the Hancock building is really obvious. Assuming this isn't just cladding, which we would never do actually. This is assuming it's structure. There's something going on here that's different, right? There's something that tells you that the structure is behaving in a way that if you look into it in more detail, you find that the loads are shared. So if we were to apply 2 loads at the top of this building through this structural system and the sharing of diagonal, horizontal, and vertical elements, you find that the reactions at the bottom are almost the same. Now, why is that important? Well, if the building is overturning, and let's say that this was the front side of the building and it was trying to turn over, you could then look at the loads due to uplift, and hopefully the weight is counterbalancing the uplift. So knowing where the forces are due to the weight of the building is super important. You define this, you can figure this out and put the forces where you want it. And in some buildings, we have higher concentrations of forces at the corners. They might be 2 big columns that we force gravity load into to resist overturning. But it's based on these principles that the tall building is like a beam. Loads are applied, there's a web, there's a flange on each side. It looks different in the tall building. It might be columns that make up this system, but the concept is the same. So for bending, we're trying to distribute the load through the webs and the flanges. Typically in this kind of situation, the web might be skinnier. You say, well, maybe these columns are skinnier. They're smaller due to the demand. And these are heavier. Okay, fine. But then the winds can come the other way. Demand can come the other way. So you have to think about it multi-directional. And so the sizing of it may not be, it certainly is not, it's not respecting a single direction of force. The other thing that's really important to us when we conceive of these buildings early on is drawing a structure to try to understand what the major systems might be. So in this case, it's a composite building. We've got a core wall that's concrete. We have steel framing. And we're introducing this idea of box sections in steel that also act to distribute air, right? So air coming out of the core could feed into these elements, and then you could distribute them into the floor system. Get rid of the ductwork, right? Just get rid of the ductwork. There's a lot of resistance to do this. And why is it, especially in places like the United States? Well, it's because the trades are different. The trade to build this concrete wall is different than the steel trade. It's different than the mechanical engineering trade. So it's a struggle to try to just integrate what we think is the best way to develop the design. You can take the core wall system in a tall building and link it to columns or a frame, in this case, by outrigger trusses. And these outrigger trusses have a kind of an interesting shape. They're just it's a triangular form. But what happens is this core wall is subjected to lateral loads. It applies load to each side through the outrigger, and the frame at the outside looks like that. So that point lines up with this point, right? And it applies load due to overturning, but it does it in a creative way. It's not a single column on the outside frame. It's a diagonal frame instead. There are 35 drawings for the Hancock Center in Chicago for the structure. That's it, 35. And this is one of them. Really straightforward. Why do we have 10 times this many drawings today when we draw the same building? I guarantee you, if we drew it today, we would have 350 drawings probably. And the reason why it's frustrating is because this is all you need to show. You have the frame at the outside. The sizes are shown elsewhere, single sheet. You have a core wall, a core system that exists within that inside frame, and you show it on another sheet as it changes. But the outside frame to it is exactly the same. And the beam sizes are shown here, column spacings are shown here. You take that same idea and you use it in a building today, it gets more complicated. And these are designs that we create, that I've created. But the core wall system, we try, or the center core system, we try to show it on every sheet, right? We have bracing elements that project from there. This is a brace core with a moment frame at the outside. It's using all steel. This is all concrete, post-tensioning. It's a tall building in Chicago. It's 45 stories tall. Shear wall building with a frame at the perimeter, post-tension beams. It's a technique to show what structural elements are. And as students, we think that this is very important. Force yourself to draw it because it helps you see other things like how does the exterior wall connect? How does the MEP work? How does the ductwork come out of the core? How does it relate to the depth of the beams? It's all super important. The idea of mixing systems, so concrete walls and steel framing. And if you look carefully at this, there's something different happening over here. There's signs of it, right? It's a frame. You don't quite know why. But if you look at the full set of drawings, you'll find that at the bottom of the building, there's nothing here. So this is a large, three-lined Varendale truss that works both vertically and horizontally to span the distance. So there are clues to seeing the structure in through the drawings that aren't so obvious when you first look at it. There's also clues when you see structure of correlation with architecture. So this is a hotel floor in a building in China, and you'll see that there is a more or less a direct correlation, I hope, anyway, between the way this layout is seen and the way the structure's shown. And in this case, it's just reinforced concrete columns and beams. There's something special happening on the outside of this, though, that is important to the building. And in plan, you can't quite get the full picture, but in elevation, you see something that's different. There's a folding pattern that happens throughout the height, and there's a diagonalization that happens. And what we did is we introduced a steel pipe that wrapped the structure. And yesterday we actually saw one of these, and I think we'll see this later, and when we look at the models that were built. One of the students or one of the student teams looked at the same kind of system that we used here. And that was not to complete the X on the face of the building, like the Hancock building, but to think about the building three-dimensionally, so that the X was completed on the other side. So this face has a diagonal member. On the opposite face, we put the diagonal member in the mirrored position, so that every time the demand came from wind or seismic, you always had members that were either in tension or compression. And the wrapping of this system was important. It wasn't just because the structural engineer kind of wanted to do something different and fun. It did many things. It held the exterior wall and created the pattern at the outside. It created a double wall system, exterior wall to inside wall. But in terms of the structure, it took what conventionally would be done in the tall building where you have a very heavy shear wall and a frame on the outside. And we were able to perforate the frame, take away a lot of concrete in here because we had the simple wrapping of steel on the outside. So why do it? Well, you do it because you reduce construction time because you have less material to place and you reduce the amount of material. So we were able to take about 20% of the concrete out of this tower by simply wrapping it with the steel pipe. And it's a conventional 2-foot diameter pipe that varied in wall thickness, and it was attached to the outside and it wrapped it all the way up. The frame in concrete was designed for gravity loads, essentially gravity loads only. The Sears Tower is interesting for many reasons, not just because it's a unique structural system, which is a bundled tubular frame. It's a series of these units that are linked together. This is nominally 15 feet on center, and it just repeats. And Sears, they came to us with this idea of the super tall building. It would be the tallest building in the world for many, many years. But how can we build that building quickly, right? So how do you come up with an idea that could be pre-assembled and then quickly bolted together? And that's what we did here, where the bending moment was very low at the midspan because it's mostly dominated by lateral loads due to wind. We're able to simply bolt the midspans together and quickly build this building in units, modular units all the way around. So today we still think about this in our buildings. You know, how do we come up with modular ideas, like things that are prefabricated where we can control quality and then get it to the job site and have it built quickly? When we design buildings around the world, we're looking for clues. You know, we're looking for inspiration. And in China, there are many opportunities to not only build buildings that are tall, but also look at cultural issues that resonate with the people that live there. Some of you may have in your apartments or your houses screens that separate rooms, right? So there's a frame like Goldsmith did, right? So there's a frame, and then the insertion is a diaphragm. A lot of times it's translucent, right? It could be fabric. It could be something solid. But the interesting thing about that is that the fabric helps to stabilize the frame, right? And in China, there were these screens that we thought were interesting. So how do you come up with a way to translate that into a building that is, you know, nominally 150 meters tall and 100 meters tall? And then actually look at two different faces, a face that expressed structure and a face that didn't. So what we did is we created this frame that looks like it's largely random and asymmetrical. But if you look carefully at it, you see lines that are heavier every 3 stories. And then if you track this, you'll see columns that go through. And those columns set up this mega frame that we then infilled. And we infilled it in a way so that it would resist loads due to lateral demand, seismic and wind. But we did it in an asymmetrical way. So this panel is braced like this. This panel is braced like that. 3 stories. And then nominally across, it's 9 meters. All right? And if you look carefully at the way we built it, we held out the elements in the structure. Why'd we do that? Because the gravity loads on the building, we wanted to be inside these major columns. We didn't want them to load up these asymmetrical frames. So we left the concrete out. So the loads, the creep, the shrinkage, and elastic shortening all occurred in that main frame. And then we went back before we put the exterior wall on it and we filled it in. So I was on a flight with one of our architects and I had this image in front of me. You look at this, you're like, my God, what am I going to do with this? Okay, it's like, it's just crazy, right? The easy thing to do would be to build a frame and decorate it. Yeah? Just put the exterior wall on it. Who cares, right? And I started to think, well, what about the negative space? You know, the space in between these lines. So this is a representation of the negative space. And then flip it to the positive, right? So make these spaces that, turn it positive so that these spaces that were dark, these dark spaces that were the negative spaces, they create these positive, in this case the white spaces, positive, and then reverse it, make the dark lines structural, and use them as infills. And this is an earlier phase of the project. This geometry changed on the infill, but the concept was the same. And then the major frame there was on the far right. That was the regular idea, you know, three modules tall and 9 meters wide. And then the structural drawing, the way you read this, is that there's something very special happening on 2 faces, but not on the other 2. The other 2 are regular, a 6 meter column grid, a typical moment frame. But we needed to tune the building seismically, so these infills acted like fuses. inside the frame. They gave up first in the earthquake so that you could protect the column and the beams. So these guys were the first ones to, let's say, fail or give up, dissipate energy through cracking and so forth. So here it is. You know, it's an expression that's different. It's an honest idea. The wall is pushed back, so there's shading that you get from the frame and so forth. So there are multiple uses of the frame. But reading it, you can tell that there's something different happening. When you read the Burj Khalifa, you may not understand it so well from the outside, right? It's a tapered form, okay, you get that. It's concrete. If you saw it during construction, yeah, okay, you get that. But what you don't see is what's happening on the inside that matters. And so when you read this structure, you see that you have these major lines that form the corridors for the residential units. And then splaying from those spines, that center spine in each direction, you see walls that project beyond that. And this is called a buttress core. The core is pretty regular all the way up the building, and it's closed and torsionally stiff. That's where the elevators are, that's where the mechanical spaces are, back of house. Everything else essentially is, there are some stairs, but everything else is your unit. And your unit doesn't have any column, right? It's all open. Really straightforward idea. It's a tripod, you know, so it's like a tripod like that tripod right there. It's a very stable and efficient way to resist lateral loads. And it's done in concrete, not done in steel. And it was the tallest building, not only in the world, it still is, but tallest building in concrete. And as it steps upward, there's an erosion of the form, and there's a transfer of loads. So the loads that are coming down from above with these smaller pieces are transferring in and moving down through the system. But everything that you see in terms of the inner workings of this building are all aligned. The core is aligned, the stepping is aligned in a way so that we don't have large transfers, and it all respects the form of the outside. Jin Mao, you can't understand what the structure is. You look at it and say, okay, it looks like a pagoda, right? Okay, fine. It tapers. But what you'll notice, though, if you look carefully, is that there are 4 points in the tower that stay in the same position all the way up. If you stand at the bottom of this building and look up, this is a straight face all the way from the bottom to the top. And if you walk around, you see the same on the noses of the other sides. So what happens is that the form erodes back in between those 4 points. And why is that important? It's because we could take a big core in concrete and link it to 8 columns at the outside. It's the first time it was ever done this way, and I'll explain what I mean. In China and other places around the world, when you look at tall buildings today, most of the buildings are using this system. And the reason for it is that it's a very straightforward idea of linking the core to the outside with these big trusses. It's called an outrigger system. You can use steel, you can use concrete for the walls if you wanted to link them with walls. But what it does is it links the core to the outside during an earthquake or during the wind, and it acts like arms. Let's say you're reaching for ski poles, right, and you're stabilizing yourself. That's the idea. The principle is not any more sophisticated than that. And then you can take that and you can create architecture in plan that's pretty good, pretty interesting. The office building at the bottom is really regular. It's like a square. And then you erode the sides at the top. Hotel, we need less space. So we erode the outside. We actually put a large atrium in the middle. All the rooms have good views. All the rooms have easy access to the elevators that exist here and connect to a sky lobby above the office space. If we tried to put the elevators in for the hotel, this hotel space above, this core would never have worked, right? So we put a couple of elevators in to get you the sky lobby, you get out, you get your key, and you move into the space above. So we're able to use this huge sort of scale with really straightforward principles and mixes of materials to create a structure that if you learn about it, you understand why we did certain things in terms of stabilizing it. And the space within the atrium is pretty dramatic. I think it's still the tallest atrium in the world. It's around 650 feet or so. You can see the elevators to the right-hand side that service the hotel. And it's a circular form inside of the octagon. And that circular form has a simple move of a projecting slab that creates this spiraling effect. But it's through this simple projection of the structural slab that we created it. Putting openings in buildings, tall buildings, is important. It helps for the winds to pass. And in this tower, which is very slender, we allowed in the broad face of the building, nominally at around 2/3 of the way up, an opening where this was used as an area of refuge for fire, but also it allows the winds to pass through. And what you see in this building is a bit of an expression of two buildings. On one face, the south face, you see this braced facade. On the north face, you see a regular frame. And we link those two frames together with trusses. So the frame on the south is really important because it resists lateral loads in the direction along the frame. But it also reduces, it helps with resisting overturning and distributing loads from column to column. So it acts almost like a belt over the height of the building to distribute the loads across. So the south looks like this. There are two towers. Well, the other thing I'd point out is that normally in tall buildings, the elevators, like I showed you before, are loaded with concrete, right? They're really strong. It's where you put all your material to resist the load. In this case, we wanted to change the idea. Make this translucent and transparent. This is where the elevators, where you'd use the elevators, the restrooms, and make it light-filled, make it lightweight. So we attached these vertical cells to the main structure, to this billboard, to create a new concept in the way you use the building. So the north face is really regular. What's important in this building is sun. So the sunlight on the south moves east to west, and actually it projects against that grid, the diagonal grid, which also helps to shade the south face. This is in Guangzhou, China, where the summers are very hot, and we're trying to control the temperature gain inside the building. The spaces are column-free, so the frame on the north versus the braced frame on the south, and you can see the way that the service is plugged into it on the back side. We used a mix of materials, steel and concrete, to create the braces and the walls, concrete walls braced with steel, and we use that for mixed purposes, as I mentioned to you before, with the walls set back. And somebody would say, well, why did you use a double line of bracing? Why don't you just use a single line? It took us a year to convince our clients to do this, because we thought it was really interesting because the braces could be smaller to resist the load, but also the impact of the way the sun hit those two braces, we found a greater shading capability of using it that way, plus it looked unusual, right? So we won the argument. We have these two smaller lines of bracing. The proportion could be such that we think is beautiful. It's quiet. The relationship with the ground is quite good. And it's a bit of a campus between these two buildings, that the base is just as important as the tower. So when we think about tall buildings, there are these things called attributes and characteristics. And it comes from behavior, right? So the Burj Khalifa is kind of a freak of nature, right? The scale of it is just extraordinary. It's just, these are 40 and 50-story buildings. Now, there are other buildings that have come that are taller. But it's the motion of the building, the serviceability of the building, in addition to the strength, that's really important when we design the towers. So we think about wind and seismic events. And just for the students that are here, you might see in a maximum seismic event, you may see 10 times the demand as the wind, right? So 10 times the displacement, 10 times the forces. We think about material, concrete, steel. And then we think about serviceability. And what do we mean by that? These buildings they're not static. They all move. And some move more than others. But for wind, we typically look at a 50-year return event for drift. And it's H over 500 over the height of the building, but also H over 500 of the interstory part of the building. And we design all the systems to include that relative movement. We typically think of wind and elasticity, okay? We don't want to have wind storms and the building becoming plastic, meaning it doesn't move back to zero, right? You want to make sure that the winds are such they're intermittent and that building is always going to come back. And a seismic event is totally different. The way we design buildings today, we design them to reach very great distortions. And a lot of these buildings stay in that distorted position after the event, which is questionable because now what do we do with the building to get it back into service? Do we have to tear it down? Can we repair it? These are all really significant questions. But you can see that the drifts are 10 times as much when you compare it. So the Burj Khalifa, that might move about 1.5 meters in the windstorm, right? But if it had, and it doesn't have it, but if it had a very high earthquake like San Francisco, it would be 10 times that much. So, 10 meters of movement, okay? It seems unrealistic, but we're designing these buildings actually to take on that kind of an overall drift without collapsing, okay? Without collapsing. Inside the building, it's super important to think about accelerations. And whether you're in an office or a hotel or an apartment, for example, these are all things that we have to think about. In an office building, we're more tolerant. You can take on more acceleration. Why? Because you're moving. You're moving around. You're sitting at a table. You're interacting with your colleagues. So your tolerance is greater than it would be if you were in a hotel or an apartment where you're staying there most of the day, you're sleeping, there's less movement around you, right? It's just yourself, maybe your family, your partner, whatever. And these thresholds of acceleration are in thousandths of a G. So they're very, very small. The inner ear is very susceptible to motion, both translational motion and also twisting motion. And it's worse when you have a point of reference. So if you look out the window and you see another building next to you and you're twisting, you're going to start to feel sick. If that building wasn't there, you may not even feel it, right? So these are things that we think about. We can calculate these. There are code equations, actually, that you can use to calculate this. But these values largely come from studies in the wind tunnel. You can dampen buildings, right? You've heard about tuned mass dampers. The structure itself dampens itself out. Concrete typically dampens out a building faster than steel, right? It's because depending on the demand, the concrete cracks, it dissipates energy, it gets hung up, right? Versus steel, which is elastic. And then we can look at other contributions like damping systems, exterior walls, inside finishes. They all impact the damping of the building. And if the damping of the building increases, that's less time that the building will take to come to, let's say, a zero state or the motion has stopped. So increased damping is good in a tall building. We talked about fundamental periods. That's the period of motion. This is the period of motion of the Burj Khalifa. So its natural period is around 10 to 11 seconds. The rule of thumb with this is basically the number of stories divided by 10. You'll roughly get the answer, right? So this is nominally a 100-story building, 110 stories, 120-story building. You can nominally get the period of a building. A 20-story building, nominally. It's about 2 seconds. Then you can do a more sophisticated calculation based on materials. Translation of steel, translation of concrete, or twist in concrete or steel. It's a way to get a start, right? It's not a sophisticated analysis, but you can get a sense of building period. And building periods are important. They get into the dynamics, the wind, the seismic. These are the periods of major buildings around the world. The Jinmao Tower, the Burj Khalifa. Jinmao that I showed you at 420 meters tall has around a 6-second period versus the Burj, which is twice as tall with about twice the fundamental period. It doesn't mean that you can't design a circular shaped building, but it probably behaves the worst in the wind because of the vortices. You could design buildings with openings to allow the winds to go through. That helps a lot. And it's a way to manage the forces, right? And again, it's the crosswind motion that we're worried about. So it's the dynamics that move the building this way rather than that way. You can see the different shapes. You can see the different factors that are against each one of these. Think of this as demand, right? So openings, square shapes, making modifications to the sides of buildings are all important. So I want to show you a couple of little movies here. Hopefully I can play them. And this is just to give you a sense of the issues of wind. So first of all, vortex shedding. So let me just show a few things that we're going to take a break. But this is vortex shedding. And the idea of vortices, the organization of the vortices around the sides, this is what's tugging on the building to make it go back and forth, right? So that's for a square shape. The other shape is a circular shape. It's more organized, and it tends to be more adverse to the tall building, right? Now, if you were to take a rectangular building, and this is one of our engineers actually in his backyard created this model. So this is a rectangular building. The fan is blowing upstream, and you can see the motion, right? It's a lot of motion, back and forth, a crosswind motion. And it's a simple model, and it's on a tuned arm, okay? It's a flexible arm, that's it. Okay, and you can see how violent it is, right? All right. Now, you take the same model and you put a hole in it. This is what happens. You can see some higher mode effects there that are happening, right? But it's pretty calm. It's a pretty calm building. So the big opening is pretty good. It's a good idea, right? That doesn't mean our architects are going to let us do this, okay? This is not necessarily what we can accomplish, but it's a good idea from a structural point of view, right? Okay, next idea, taller building, but put slots in it. It's better than the shorter building without the slots, right? Let's try it one more time. So slots are good, and they're good because you can use them for other things. You could actually generate power by allowing the winds to go through the side and putting a turbine on the sides, right? Just an idea. Now, you can dampen buildings, all right? The one in the back has no damper. The one in the front has got the damper. And it's a sloshing damper. So it's a simple enclosure with water inside of it, right? Let me play it again. And you can see the direction of the damper. It's along the direction of motion in this particular test. So it's dampening it out. The building motion comes to a halt much sooner. Now, what if you turned it? No, sorry, this is still in the same direction, only the geometry is a little bit different. So it's a bigger cell, and it's sitting on top of that rectangle that I showed you guys earlier. But it's doing a pretty good job. All right, let's look at it one more time. So there it is along the long direction of the rectangle. Not bad, right? Okay. So now, what if we took the same tall building and we turned the damper? Okay, we put it in the other direction. What happens? It doesn't work. Yeah? Because the period of the damper itself now is not in sync with the period of the tower, and you're actually getting an increased impact. Now this is tricky because tall buildings, motion's in multiple directions, right? This is just a little model. But what you have to do is you have to tune that damper to the period of the building in each direction. So if the period is different in the other direction, then you've got to activate it in a way that allows for both directions of motion, but with different periods. Now, what if we made the tower into a pyramid? All right, so this is a tapered shape. Now, what's happening here is the fundamental period is not dominating. It's not moving very much initially, but the higher mode effects are amplifying the demand. So you can get an earthquake, for example, or even a windstorm that would aggravate those higher modes and actually create much more demand on your tower than you might expect. And codes typically don't address this. Okay, that's the trick. They typically don't. You saw earlier you put a higher force in some earlier codes. You put a higher force. We're trying to account for it, but it's not super accurate, right? Then we also talked about upstream buildings. So there's the rectangular tower upstream of the other tower, of the pyramidal tower. Now what's happening is that it's aggravating it and creating the fundamental, it's activating the fundamental period of the building, and the higher mode effects aren't that big, they're not that big of a deal, right? But look at what that tower did upstream of the pyramid. So anyway, these are all things to think about, and they're qualitative, at least in the diagrams, right? They're qualitative. But when we design these buildings, you can at least start here and then verify it later on with more sophisticated testing and analysis. That's what we have right now. I think we're going to take a break, right? I don't know if anybody has any questions. If you have any questions or thoughts about the stuff that I think I showed here, a lot of it is the fundamental stuff in terms of design. And when we come back, we're going to take a little break and come back and first talk about, I think, yesterday? Yeah, okay. So we're going to talk about yesterday with some testing that we did. It's kind of fun, so those of you that weren't part of it maybe want to see that. And then we're going to talk about some more sophisticated thinking in tall buildings, issues of performance, the impact of nature on design, and maybe some ideas about the future. So that's kind of what we have. So earlier we talked about really the basic fundamentals of design. The site, fundamentals of form, loading, reading structures. And now we're going to talk a little bit about systems. And a few principles to think about. One is that one of the best ways for us to start is what we've done before, right? So the frame, the tubular frame, was a good solution for tall buildings, but we think that ideas like the one that you see on the far right might be more efficient. And why is that? Because the structure is broken down into what is essentially tension and compression elements. So everything is either in tension or compression. Nothing is really bending, right? So the beams and the columns bend in this system, and they don't in that system. So if you were to achieve the greatest efficiency, it's one that you have almost no bending in the superstructure itself. If you take these two diagrams of systems, and if they acted independently, the moment of inertia would be far less than the moment of inertia if you assembled them together, right? So that's what the Sears Tower did. It took individual components that had moments of inertia and combined them together to create something that was much more significant. When we talk about tall building design, there are two things that we think about in detail. One is gravity load, and its impact on material quantities. And the second is lateral loads. And it could be wind or seismic. But you can see that as you build taller, the amount of material that you need for the gravity system increases linearly. It's fairly flat. But for wind or seismic, it becomes asymptotic, right? So the idea is coming up with systems that drives the quantities down for the lateral resisting system. So when we designed the Hancock building, it was one of the first times that we used computers to analyze the structure. We created substructure models of the building that verified the hand calculations. But Fazler Khan was an important part of taking the application of engineering, the science, and applying it, and the use of computing to actually speed up the process and come up with a dual way of getting the solutions. When we talk about steel systems, they're like species of animals. So based on size and scale, the species is going to change. And so when we think about shorter buildings, we might think about frames that resist lateral loads. And as we get taller, the system changes from braced systems that are connected from the core to the outside to that mesh idea that I showed you earlier. These are ways that we might deal with very tall buildings and ways that we might deal with the efficiency in design. In concrete, you might start with a frame, introduce shear walls, combine the shear walls with frames, create frames out of the concrete perimeter that might be diagonalized, and then use systems that are braced to the core or use systems that are diagonalized. Being careful with the one on the right-hand side because of the ductility issues that you might be challenged with if you were in an area of high seismicity. But nonetheless, the idea of diagonalization. You could take the combination of concrete and steel. So these are diagrams that look at concrete cores and perimeter steel frames, or frames of concrete that are wrapped in steel and so forth. When we think about systems, it's beyond the building, okay? It's part of the urban plan. And what you see in this model is areas in dark blue of these towers. These are areas within the towers that we're predicting that the amount of usable space is below the threshold limit. So let's say that you wanted to have 80% of the space occupied. For these buildings, because of their geometry and the type of structure that we imagined for them, as soon as you got through the transition of blue, you were in an area where you were less than 80% occupied. And this is important when we plan cities because the geometry of these buildings can be changed. We can change the materials. We can make them more efficient. So when you layer in elevatoring and structure and so forth, what's left over for usable space is really important because that's the leasable space. We've been looking at various parametric models that look at form, building efficiency, that's the occupied space that I just mentioned. Carbon. We talk a little about carbon at the end. This is carbon inside the building. This is embodied carbon in the structure. We can think about other things that are non-structural, right? Like solar, the exposure to sunlight and also views, and then finally structures. And we can think about this all at once, right? When we're looking at different forms. And create systems that are different, they're unusual, they're more organic than we might have seen in the past. And this is where we've been looking. We've been looking at nature, and Rosa's here, and she's an expert at the translation of nature to structure and architecture, not just from the point of view of what it looks like, right, but how can you sort of dissect it and create structural properties that are buried within natural elements that help us with the new ideas for tall building design. So bamboo is an interesting example. If you look at bamboo, you'll notice that there are a series of rings. But you'll also notice that they're not evenly spaced. Now, in bamboo, the structure itself is actually hollow, but the rings are diaphragms. Okay? So, why are they unevenly spaced? It's because when the bamboo gets subjected to wind, the demand on the wall increases as it gets to the bottom. The bending moment increases, right? So the rings are placed in such a way that it prevents the walls from buckling. So the tighter the spacing, the higher the capacity. You know, Samantha just showed the unbraced column. Same idea. Brace it more frequently, you're going to get higher capacity. Same section size, but if it's braced more, right, higher capacity. You can take these ideas and look at aspirations, right? From the Mile High Tower to Foster's project for the Millennium Tower to Rosa's project for the Bionic Tower, creating ideas of cities within structures, right? But coming up with systems that are really efficient, structural ideas that use the whole cross-section of the building to withstand lateral loads. So Einstein was a mathematician, but also was inspired by natural form. And one of the quotes from him said, I discovered that nature was constructed in a wonderful way. Our task is to find out the mathematical structure of nature itself. It's the kind of faith that has helped me through my whole life. So this is a stork's bill seed that dries in the shape of a golden spiral, and what it does is as it dries, it corkscrews itself into the ground to ensure growth. So this shape is mathematically predictable. It's a product of natural form that, in this case, ensures growth while it's actually drying. Instead of growing, it's drying, right? So bamboo, with its hollow form, is interesting because of the idea of the diaphragm, but it's also interesting in its cellular structure. The structure toward the perimeter of the wall, so out here, the cellular structure is more dense than the inside. Why is that? Well, it's because we're trying to push material to the outside, right? So naturally, that's what's happening in the growth of the bamboo. The other thing that's interesting is that there are quadratic equations that people have discovered that consider the growth of bamboo. And these quadratic equations, when you plot them vertically, you find that you get a curve like this. And this curve is similar for the diameter, the wall thickness, and the spacing of the diaphragms. And if you look at it, when you plot that, in this case, it's the wall thickness over its height. So this is the height of the building, and this is say the diameter. You find that it's quadratic equation, and you find that it's a very similar equation that you see for the bending moment of a cantilever subjected to a constant load. So the characteristics of bamboo are directly connected to the mathematics of how you actually engineer structures. Makes sense. It has to make sense. So we looked at this, and we think that there are ideas that are important to consider. And as with the spacing of the diaphragms in the bamboo that are not even, perhaps the spacing or the outriggers or the diaphragms are also uneven. Tighter at the bottom where the demand is the highest. Yesterday we talked about outrigger placement and the idea of locking the base of the building in a more substantial way. That's the idea. But you can actually take it and apply it to buildings of various heights and incremental systems that have a mathematical basis to them. So this is a proposal for a tall building in China, in Beijing. It has not been built this way. It was built, but not with this system, where the outside was similar to the Hancock building, for example, and the inside was a form that varied in shape. And then we interconnected the inside to the outside to form a double skin and the architecture that you see in the image on the right. The segmentation's elsewhere in systems, right? So the dragonfly, the body of the dragonfly, the idea that there's a hollow section, it's braced with diaphragms, and the bracing changes along the length, depending on demand. And you can imagine if you took these and stood them, you might think of them as systems of tall buildings, right? Point of support and diaphragms along the height. We design buildings based on what we know at the time, right? So this building in San Francisco, the Alcoa building, is a concentric braced building. It's an area of high seismicity, but it uses this principle of a uniform structure that's there to resist gravity and lateral loads. But we wonder about ideas like the Fibonacci sequence and what it might mean to the mathematics of structures. And the Fibonacci sequence is interesting because it's an increment of numbers. The number that happens in between is a constant, more or less. So between 13 and 8, 8 and 5, and 5 and 3, the constant is about 1.6. And if you plot this and you continue to run the numbers out, you find that the summation of these two numbers gives you the next number, so it'll be 21, right? And then 21 plus 23 gives you the next number. You'll find that that constant becomes more and more exact, like pi. As you take pi out, it becomes more and more exact. It converges. Well, it doesn't converge. It never converges, but it tries to converge. That same principle is in this. The same idea is in the hurricane, right? Or the typhoon. And we, for years, have been thinking about the typhoon or the hurricane, the mathematical principles that help define this. And we wonder whether or not we can take this idea and instead of thinking about it like an applied force, we think about it as a resisting force. And we think about it not flat, but vertical or volumetric. So imagine the eye, which right in the middle of the eye, there's no force, maybe no resistance. But as soon as you get to the wall, that's where you have the highest force or inversely the highest resistance. So that's the concept. It's the basic principle. So how does it work? So how do you take this and now think about a building, right? Well, I don't know. You might think about the structure being at the perimeter of the building in some organic way. The inside is whatever it is. It could be an atrium. It could be usable space. But then you take the principle of this mathematical definition and you try to define it over the height of the building. So if you look carefully at this, you'll see that the spacing at the base of this tower for the frame is smaller and it's more horizontal. And in this building, the idea is that we have a gravity frame wrapped with a steel lateral load resisting frame only. Sort of like that tower I showed you earlier with the bracing that was not a complete X on each face. Gravity wrapped with the lateral system around it. So you can have fun with this, and you can think about systems that maybe are much more organic, much more than we see them today. So, there's some flaws in this, right? Curved members. They might be beautiful, but there's an eccentricity, right? So we were talking about eccentricity before with load. This is an eccentricity of applied load and placement of material. Okay, so there could be straight members in between, but nonetheless, you create something that is based on the principle of mathematics. In this case, trying to take the Fibonacci sequence and incrementally plot it, not horizontally, but vertically, and create a form that might save material. So if you add these forms together, you come up with these braced systems that you didn't think about before. But it has the basis of an idea that could save material. And when we analyzed this building, we found that you could save about 20% of the steel in the perimeter frame because of this organic transformation from bottom to top. And what you get out of it is something that is futuristic and maybe buildable in the future. It's a little aggressive in terms of the scale, okay? I mean, the member sizes are a bit too small in the rendering, but you get the idea. When you take elements and they're subjected to tension and compression only, you can assemble a mesh. And if you took that mesh over the height of the building, you find that the scale is quite beautiful. This is a floor to floor, and the scale of this is such that you can connect and resolve it even with complex plan geometries. and create something that's always in tension or compression. So Fazlur Khan, in his writings, you'll find that he thought of the perfect structure, which was solid, a solid tube. Well, this doesn't work for a tall building, obviously, right? So you start to put holes in it. Circular holes are best. That may not be appropriate for an architectural solution that's acceptable. You start punching it with rectilinear holes, and then you end up with this idea of the tubular frame. But if you start there and end there, is what our hope is that there's an evolution in the progress of systems, and this idea might be much more efficient. So why is it more efficient? Well, a couple of things. The tension and compression is true in every single element. But in addition to that, what happens is the load tends to wrap around the system in a much more efficient way. Now, what do I mean by that? So as the winds, let's say, move through the building, and let's say the building is translating up and down, what you want to do is activate the flange. So in a column-based system or a frame-based system, the load grows in the web, and then it tries to go around the corner. But you can't get the load quite out to the middle. It's a phenomenon called shear lag, because there's an inefficiency in transferring the loads through the frame to the column in the middle. So you get about half the load there that you had on the corner. But if you created a mesh, you increase the efficiency quite a bit, almost 50%, by using the diagonalized system to move the load to the middle of the flange. And you can imagine if this grew, it becomes less efficient, certainly less efficient here. So there's a geometry change. The tighter it's together, the higher that value would be. But what's really important is that the deformation due to column shortening, either tension and compression, is essentially the same as the total displacement of the building. Bending's bad. In a tall building, bending's bad. Think about that. If you can reduce bending, you've done the best you can. So, here's the answer. It's an idea about systems that form itself to a geometry that's complicated. So when we designed this building in San Francisco for the competition, about 9 years ago now, it's called Trans Bay. And what we did is we conceived of the building with a new kind of concept. We didn't win this competition, we lost. In fact, this building's built. It was designed by Cesar Pelli, totally different idea. But we used it as an opportunity to sort of exercise the ideas of natural form and come up with what we thought was a pretty creative approach to a tall building. And it caught the interest of people, including a man that I knew. He's now moved along from the Bay Area, but he was the head of the theological seminary in San Anselmo, California. And he spoke about this project to his incoming students. So the seminary students, as they were coming, he mentioned that, what if we could coexist, right? So what if structures could coexist with forces, with people? And one of the quotes that he had was, one of our strongest human instincts is to try to stand up against what Otto called numinous, the unknown and compelling, but also frightening mysteries of the creative forces of the universe, to resist their energies so powerful that they can make us feel insignificant in contrast. The idea of resistance, right? Everybody thinks that you must resist, right? You must resist wind, you must resist seismic. But it's more of a philosophy about coexistence that we think is important in these designs. So buildings of various forms, the regular form on the right, this more complicated form on the left, thinking about a building as an overall unit. Forget about beams and columns. Think about it as a membrane and look at it analytically with unit loads to see where forces are flowing. The areas in the red are highest, the areas in the blue the least. And what we wanted to do in this building was actually to create an opening at the bottom, to go through it. The first architectural sketch, we were meeting with an architect. We described what we thought was the force flow. We worked together. He created this. It was an initial idea of taking Mitchell, which is the truss to the right, and trying to come up with a superstructure system that pushed load to the outside so we could create an opening at the bottom in both directions, the broad face and the narrow face. And this was a system that we thought could be resolved and interconnected along the height. And it used the base mathematics that were here in the hurricane, the stork spill, the Nautilus shell, spider web, and then trying to come up with this intrinsic architecture that Phil Butin talked about of coexistence, and what about the idea of architecture being like the hurricane, right? And the idea of 2 points of support and a single point load. This is the most efficient force flow that you can develop. It leads to the least materials, and it's not straight, okay? It's a bulbous shape. And this is the principle that we use to develop the frame for that structure. And what we did is we assembled it with the 2 points of support, a common angle, 85 degrees and 90 degrees, and we created and stepped the frame and built this geometry based on the mathematics of Mitchell, and then created the segmentation that appeared over the height of the building. We interpreted it based on the geometry of the tower, and then we sliced it on the broad face and on the narrow face. Not perfect, right? Because the bulbous form would have been the most efficient way to do it. And then resolved it, every single interconnection point on the folds of the tower to create a continuous frame. So what emerges out of this is something that is really quite, we think, quite beautiful. The base of the building is office. The top is residential. And look at the density. The density is less in the frame at the top where you want to have more sight lines and light. And it's less at the bottom where maybe people don't care as much in the office space, right? You're at your desk, you're working throughout the day. The form at the bottom is much more regular than at the top. You could express the structure, right? At the bottom, in this case, what we did at the bottom is we pulled it forward. At the top, we recessed it back, and we had actually balconies and things that would project from it. We could take this concept of lateral load and gravity load and balance it so that we're resisting overturning. And this was being developed post 9/11. So people were asking what happens to tall buildings when they get impacted by man-made or natural disasters. And what we found is that there was a great deal of resiliency in the system, so you could actually remove elements and it was self-healing. The forces were flowing around it, both for gravity load and lateral loads. So we found that it was actually a very good way to solve all the problems that we were faced in the tall building design. When we think about tall buildings, we think about motion, right, and earthquakes. So in Kobe, Japan in 1995, I was there, and if you take a look at this image, you can see that there's something that's happened to this tall building. There was a disruption, right? It was, 7 or 8 stories up. There was a column failure like we saw in the videos. And it was because there was probably a change in stiffness in those vertical elements. What a lot of these buildings incorporated was structural steel buried in concrete for the lower portions. And then what we believe is that they didn't stagger the structural steel in a way that allowed for a smooth transition of stiffness. So they were quite stiff near the bottom, and then there was an abrupt change where there was a change in stiffness and actually a shearing and an instability that occurred at those levels. We also saw very large ground motions, amplification through soil. So we talked about building period, and we talked about the impact of sitting on rock. When you sit on soft soils, the earthquake gets amplified, right? So if you have shallow foundations like this building, you can see that it's disrupted by the motion of the ground, and the soft soils are amplifying the demand. So this building was City Hall, and it was City Hall that actually transitioned to an office building. This became the new City Hall here, the taller building. But you can see that there's something that happened to this building that's quite unusual. We lost the entire floor. I think it was the 4th floor. And it was because of that change in stiffness, I believe, that happened there that the entire floor pancaked. Now, it wasn't a progressive collapse. The entire building actually didn't come down. And I visited the site about 8 years later, and this is what I found. They reused it. They chopped the top off, and they created this structure, okay? So, okay, there are ways of adapting and ways of thinking about this that are super important when we talk about buildings and resiliency, right? And when you talk about tall buildings, there are these challenges. We talk about an outrigger system. It's a great idea to link these two together. But during construction, you want to let them breathe, right? You want to let the building breathe. So my daughter is now 29. She lives in Scotland. She's an artist. And you know, I look a little different. But popsicle sticks, tongue depressors, these, with wood dowels. And these dowels were placed in the structure, and then there was a slot put in the diagonals. Why? Because so the thing would move. So how do you make a structure that's huge in scale move during construction? Because this is creeping and shrinking and elastically shortening more than this. So if we don't do that and we lock it all up, it'll tear that truss apart, tear it apart. Now you could say, well, I'll just leave this out. I'll leave the diagonals out. That's no fun. Like, okay, you could leave these out and put them in later, let the building go ahead. But that was no fun. What we wanted to do is actually put it all in place so the construction could continue up in a unified way. So we created these pins in this truss system. This is the working drawing. This is at the fabrication plant. And this is the scale. This is one of the joints. You can see the pinhole. There it is in place. The idea was the pins were put in. There were some temporary bolts that were put in. You can see it for fit. But those bolts were taken out. The pins were left in place. It moved. These huge members moved during construction. And then we put all the bolts in. They're all oversized holes. And we calculated that the geometry was such, the change in geometry was such that you would never violate the two oversized holes that were overlapped on top of each other. You could always get the bolt through. Anyway, that was the idea. So here it was with the mix of materials. We talked about this earlier. But that idea of creating this interconnection that allowed for movement was important. So the building is very successful. In fact, it just celebrated 20 years after being built and occupied. It's a commercially super successful building. But it was a challenge to build it, challenge of ideas. And it used these 8 columns, those 8 big mega columns that I showed you earlier, and the linkage of those 8 columns to the core as a structural system. In Chile, in fact, this is south of Chile. This is the Isle of Chiloé. It's a beautiful place. This is around the same time as the Kobe earthquake in the mid-90s. And I went there and I visited this town, beautiful place with churches, Jesuit churches. And I discovered that these churches, a couple of things. One is the churches did really well in an early earthquake in 1960. There was a huge, in fact, it was the greatest recorded ever. 1960 Chile, you can look it up, 9.3 on the Richter scale. These churches did fine. They survived it. They weren't really damaged very much. I was traveling there after a symposium kind of like this. And, you know, it's one of those things where you go and you give a lecture and then people say, well, let's go on a little trip, you know, and you know, everyone will kind of go. That's part of the presentations. And I found that there was only one other person that wanted to go, in addition to me. And that was Richard Tomasetti. As many of you may know Thornton Tomasetti as a firm, engineering firm. So Richard was part of the founding founding two fathers, so to speak, of the firm. And he was dating a woman at the time, so she's there. So Richard and I, his girlfriend at the time and an architect traveled around and looked at these churches. And I went up inside here and I found that inside the church and all the trusses were these wood dowels. All the connections were done with wood. No metal fasteners. I thought, wow, that's pretty interesting because guess what that does, right? This is like a pin that could rotate, but there's friction, right? Or it could slide in a slot, but there's friction. And I was convinced that that detail protected the structure from damage in the earthquake because it fused the joints. At one point, it allowed the joints to rotate, but not freely, not loosely, right? But there was a restraint, but it didn't lock the joint so the members failed. So that was the impression I had. About 10 years before, I was at Lehigh University, and I was testing these beam and column connections. And they had bolted webs, flanges that were welded. I kept thinking, it doesn't make sense, okay, to take a structure and put it through cyclic motion like this and fix everything in a perpendicular fashion. And you can see the stress concentrations at the face of the column. It's not natural, right? It doesn't make any sense. These welds broke. This was testing that was done for the American Institute of Steel Construction. It was at the tail end of a testing program. People were tired out. I was just a kid in college, graduate school, and I'm writing about these and saying, well, this is not really a ductile connection. This is kind of brittle, but it's safe. You can see that there's deformation in the column, but the energy is dissipated here. The structure doesn't fall. This is 1985. 1984, 1985. 1994, in Southern California, it was something called Northridge. And for those of you that know about the Northridge earthquake in the United States, steel frame buildings did exactly this. So what happened was we had proved to ourselves that the buildings would be safe, but they're not very resilient, right? So there's a lot of movement now in the community to create more ductile connections, yeah? But I would argue if you could create connections that are more elastic, that's best. So if you take this idea of pins and friction, whether it's a frame or it's a rectilinear frame or brace frame, and created systems that were more like your body, where there's a pin in the beam through the plate, and there's a curved plate. And then you clamp it together, okay? There's a friction material here. So based on the clamping force and the friction material, you know when it's going to slip. It's pretty straightforward, right? F is equal to mu times n. It's it. Simple. You can calculate when it will rotate. It stays fixed for most of its life. Yeah? So wind, moderate seismic, it doesn't move. Big seismic, big bending moments at the face of the column. Instead of damaging the beam, this thing rotates. And it dissipates the energy through friction and heat, like it breaks in your car, right? And so you use these kinds of components that are basic components that you see in the building industry, and you create frames that look like this, rather than everything's all welded up. I don't know. I mean, it's an idea. It's hard to make people build this, though. They don't really want to build it. It's too complicated, or whatever. I don't know. It's not that complicated. But here's the frustration of design and construction, right? We're getting there. It takes time to convince people that this is a good thing. So you have systems that could be components, like we were talking about pre-assembly, right? So you could build the arms and then bolt the center. If you have bending moments in the center, maybe you have to put top and bottom, connections. Unlike Sears, if this is a long beam, say it's, 30 feet long rather than 15 feet long, you're going to get bending moments here. So you may have to lock it up, but if it was a shorter span, maybe you don't need the plates on the top and bottom flanges. So instead of damaging the structure the way we design them today, maybe they fuse. And you try to keep the system elastic. Keep the column elastic. The only inelasticity is through the friction, dissipation of energy. This is elastic. And you don't fuse them all at once. You design it so some of them fuse, and the others tend to pull it back, right? There's elastic energy in the system. You can use pins in other places that you don't expect. Building in China, 90 meters to here, 60 meters to here. There's a museum, office building. What we wanted to do is create the largest, almost structure-free glass wall in the world. The largest cable net in the world. That's what we wanted to do. Now, we didn't start that way. We started with trusses, you know, like what you typically do. Well, we'll put trusses across here. We'll hang them from the top. They'll span across. Some of the early renderings, you looked at the inside of this atrium, loaded with structural noise, right? So if you were to create a glass wall with cables and try to span 60 meters by 90 meters effectively, it moves way too much. It's almost impossible. You just can't design it. So instead, we said, well, why don't we use the cables here and here and connect it to the top of the museum and form a way to allow for the glass wall to be braced. That was kind of the idea. What happens when you put this here and here and here in an earthquake? Well, it becomes a braced frame. And what you find is that you can't design the cables anymore because the structure is so huge. It just pulls it across, right? This huge frame moves it. You put more material here, still fails. It tracks more force. So what to do? Well, we have a problem. We've got a huge problem because we convinced the client that we have this cable net. He loved it. Oh my goodness, this is awesome. This is like, wow, great. We go back, like, holy crap, like, we got a problem. We have a problem. And the forces flow like this under gravity, right? Up and over. So we thought of the pulley. If you have a pulley, then the forces in these members should, if it's symmetrical, should not increase, really, except for a friction in the pulley. Should be the same. Now in our building, it was more complicated because the position of this support was not in the middle. It was offset, yeah? So it's not perfect, but the idea was to use the pulley. So we went to our architects and said, we want to use a pulley. This is 10 inches in diameter cable, and in order to make the cable work around the pulley has to be twice as tall as this room, okay? Huge. And we said, well, wouldn't it be beautiful to see that big circle there, like this big pulley? The architects were like, get out of here. You're not gonna do that. It almost looked like this, you know, like huge. So what we did is we tried to think about how would it behave? Concrete. I showed a plan of this building earlier today. I talked about a system of a Varendale. It was actually on this side of the building and the concrete walls. So anyway, the building itself was fairly straightforward, but here's the problem. So we got the high strength cable. This is actually supposed to be pointing here, 220 millimeters in diameter. And there's the cable net, 34 millimeter cables on a horizontal, 26 millimeter cables on a vertical, and we needed to use this system to brace the wall. It still moved about 3 feet in the wind, in the 50-year wind. But instead of the pulley, what we did is we used pins. And if you were to take a look outside of your window at the top of this cable net and look down, this is how tall it was. So this is the window of our office in San Francisco, 24 stories up. That cable net was that tall. Or is that tall. So here it is in scale. So there are people cleaning it. What's really interesting about this building is that there's this sort of interconnection between occupied space and space outside of your window. It's sort of like a organic sort of pattern of city movement. So it's a pretty interesting concept in addition to creating the atrium. Okay, so here comes the pulley idea. But then here's the pin idea using principles of allowing the motion like Jin Mao, using 3 pins and then a 4th pin to allow for movement in the other direction, right? Because the building could move this way too, it could rotate. So this model was used to study the behavior of the joint. If these elongated, we had force. If they didn't elongate, no force. Pretty simple. So you could move this frame back and forth, and in fact, you'd find the spring didn't really elongate very much. Stayed pretty constant. So it was a pretty good idea. So if you look at it in motion, it looks like this. It's asymmetrical. The arms are different because it's not in the middle. Slightly off. The model became, sort of like, it's a better version of the popsicle sticks, right? And this is it's a little bit nicer. And anyway, that's what you get. Okay, so the ideas of motion, right? Scale, in this case, really different. This is the architect next to me, Brian Lee. You have to sort of have will and ambition to do something like this. The cable net is still the greatest, tallest in the world, but it's a systematic approach to dealing with glass and seismic movement. And you can see that there's a little bit of imperfection, in the wall. There's a little bit of pillowing, because actually this point is not flat with the glass, it's pushed in. So we had a combined effect of the diagonal supports stretching the cable across those big other cables and then pulling them. And when we did that, we found that there was some out-of-plane movement. So the planes, the 3 planes of glass, are completely flat. And if you look at it from the inside, it's a highly nonlinear problem. This is the main cable. This is what it looks like if you look up the cable. And what's happening is that the wall, when we stretched it, was pulling that cable out of plane. So we had to engineer every single link in a way that in its final deformed condition, we were as flat as possible on the outside. Flat as possible. Not an easy thing to figure out because you have a lot of different things going on between the demand in the cable itself, had a certain level of pre-stress in it due to the weight, right? So you had to calculate that relative to the amount of pull that we were putting on it, and we did it incrementally to get it into position. But it's a way of taking the problem that we sort of created ourselves and turned it into something that is pretty unusual, and it works. So back to this tall building. It's spaces that you create, residential spaces, the ideas of structure that are pretty simple. Core wall, in this case concrete with a steel frame. The idea of actually using link beams in the concrete shear walls that were fused using a similar concept that I showed you earlier. In this case, a butterfly pattern with the steel plates clamped together and then designed to move when you get a big earthquake. Link beams in tall buildings, they get damaged. And if we can prevent the damage in the link beams, they're the sacrificial piece typically in these taller concrete shear walls, then we have a more resilient structure. So it uses the principle of friction and clamping, and then it will move when the demands are super high. You could also use this in frames that are braced, like this one, and use circular hole patterns to allow for the rotation. Testing of it is important. This is at the University of California in San Diego. Hang on a sec. One other point about resiliency. So our concept for the train station next to that tall tower at Trans Bay was to seismically isolate it. It was a fairly brittle steel structure. You could see it here. Not a lot of ductility in the system, so we put the ductility at the bottom. We seismically isolated it. So this was our idea, the rendering of what this building might be. And it looked like this on the inside. We thought it was a pretty spectacular idea. Again, it wasn't picked, but the ideas there and in the tower were important. So the base of the tower was imagined like this, where the loads were coming out. The cores were set back. Those two core walls that I showed you in plan were set back, but you could pass straight through into the train station. And the relationship was interesting at the street level on both sides. We had the same principle of the arch. We were talking about the arch earlier, to move the loads around that long span and create this tower. So that was our idea. I'm going to skip through this piece. There's a piece in the book that talks about performance and performance-based design, and it's largely seismic design, and it's based on the principle of using higher levels of engineering to deal with buildings. Typically, and I'll just show this image. In San Francisco, there has been a move to reduce the amount of construction in some of these taller buildings by eliminating the frame that by the convention of the building code would have to be there in addition to the core wall. So the idea is to solve the building outside of the building code by using what we call as a core-only system. And all the lateral loads are taken by the core. In a traditional sense, it would be shared by the frame and the core. But there's been techniques that have been developed and guidelines to allow us to engineer systems that are core only. They're less redundant, but they're more carefully looked at. So this is an example of a building in San Francisco that used this technology. This is a rendering, but the building's actually built. And it uses a core-only system, gravity columns on the outside. It uses special detailing around the columns for the slab. But that's the lateral load resisting system. Typically, if your building is, at least up until very recently, if your building was 240 feet or less, and was symmetrical, you could use a core-only system. If it was greater than 240, this is a pretty symmetrical building, then you would have to put the frame in unless you could prove otherwise. And that's what performance-based design allows us to do, to prove an equivalency to the code by using just that singular system. Okay, last thing I want to talk about is the environment. And this is Trans Bay, actually. This is just a ghosted model of that building. And if you remember back earlier today, we talked about the soil conditions and so forth, and the fact that this sits actually in the water, the original water line. But the reason for thinking about this, and we were thinking about it at the time that we designed for the competition, is that the carbon that's emitted the first day we build is sometimes more important than the operational carbon. In fact, if your building is substantial, let's say it's 15 to 20 stories tall, it takes 20 years for the operational carbon to overcome the carbon that you put in the first day. So we've been saying to the community, we need to focus on carbon in structures, because if we can reduce this, then we reduce the impact, and in many cases, we can reduce it for many, many years to come as you compare to the operation, right? So for example, if this building came out of service before 20 years, this would be the most important thing. The other thing I'll say is that there's been a lot of work that continues to drive the operational carbon down in buildings. So this becomes even more dominant when we talk about, the efficiency of mechanical systems and so forth. We drive the carbon down. The embodied carbon the day we build is really important. The other thing that's really important is what we do with this, right? Waste in systems. And a lot of times people say, well, this stuff gets recycled. Forget it. Most of the time it's not recycled, and because the material itself can't be recycled, many cases it's downcycled once. We use it once, and then we put it into landfill. So for instance, we might build clothing or decks for your house out of this material that is plastic, but then it ends up in the landfill. So we've been thinking a lot about the environment and how it might impact our structures. And we're probably at a tipping point. We're at a tipping point for climate change and the temperature rise that's happening on the Earth. But I think we're also at a tipping point in the way we are polluting the Earth. So how do we take systems in a smart way, right, and incorporate it into our buildings? So if we could put waste into our structures in a smart way, get rid of the concrete where you don't need it, right? A lot of times when we build a two-way slab, right, here is two-way slab, we load it with concrete everywhere, right? But all of us that we've engineered a two-way system know that the concrete in the middle, all you need it really is to bond the reinforcement top and bottom, and you could create voids out here and get rid of the material where you don't need it. Here you need it for shear, right? So the idea might be that you replace the concrete with lightweight material. We had the crazy idea of using water bottles that were empty, right? Air, trapped air. Put the cap on it, put them in cells, put them in the structure, make it lighter. You can make it out of these blocks because, you know, the water bottle is a good idea, but it's a little bit hard to work with them. You can put it into conventional buildings like this one and create these ideas that seem far-fetched, but we think that people start to get interested in thinking about how you might use materials inside structures to make them behave better. Lessen the mass, reduce the concrete, do it with flat plate construction, top and bottom, flat plate, right? No beams. Reduce the weight on the foundations, and then the seismic mass, as we talked about earlier, gets into the lateral system like the core walls. Save material. Concrete, steel, make it more efficient. That's our hope, okay? It hasn't been built yet, okay? That's another idea. It's not built yet, but we hope. Okay. How do you calculate carbon? Super important. Carbon is based on lots of material types. It's based on material, it's based on construction, and it's based on how buildings perform. Those are three of the main characteristics. So back to the city, and as we think about the city in these parametric models, and back to this carbon calculation, which we think is really important. This is the embodied carbon. And what this diagram shows you, in blue is material, red is construction, and yellow is what we call probabilistic damage. So areas like San Francisco where you're going to get damage in time. You can go on our website and actually run this program. This is a program where you input the number of stories above the ground, below the ground, the area of the structure, the material type. It'll tell you what the average floor to construction time is. You can change it if you want. And it asks for a service life, let's say 50 years. Then it also looks at wind and seismicity. And seismicity is important because of the nonlinear behavior we talked about earlier. If it's a conventional system and it's life safe, that's the minimum requirement. But what you can do is the program allows you to look at how much material we believe would be in a 50-story building in an area of high seismicity. It calculates the amount of steel that's required for this structure, how long it takes to build it based on the assumptions that you give it. And then you can get into the carbon that's associated with the material, where it's coming from. The program looks at that. It looks at how many people we think needs to be there to build it, the travel time, the people, the distances, all that stuff is there. And it comes up with a value that you can equate to other things like the power for homes or fuel for cars. It's a way to bring it to people so that they understand it is a big deal, okay? It's in our buildings. So, you know, we think about this in the future and how we minimize material, increase performance so that carbon that's associated with damage, the pie gets smaller if you have special joints or seismic isolation. It's based on principles rather than maybe what we've been told in the past, that ideas of the strongest remains. So systems of optimization for towers, looking at forms, membranes, volumes, applying loads, points of support, areas in red are highest demand, blue less demand, interpreting this into frames that may look different, right? It's all part of that idea, like you're really trying to start over almost. Use the fundamental principles to come up with your ideas. And then create these structures that are unusual, right? But I think with the technology that we have, with the definition of drawings and the idea that drawing and construction gets a lot closer together, right? What we draw in the future, I believe, is going to go straight to the contractor. There's not going to be shop drawings and other intermediate kind of drawings. It's going to be a straight run from design to construction. Maybe some of these things are more achievable because we have more control, right, of what happens between the designer and the builder. So anyway, those are some ideas. It's all based on that book that I showed you. You can find all this stuff in that book if you're interested. It continues. It's an experiment, right? We experimented with those towers yesterday. We learned something. I think all of us learned something, and so we try to build on that. But that's what I have in terms of the kind of ideas that I wanted to share with you guys. More to come, I hope. In terms of what we develop and ideas that get pushed out that people are thinking about. It's how do you interpret all that, right? And students that are here, take this stuff and run with whatever it is, and use it or not use it, but create something that's good. That's important. Yeah, it's important to do. So, thanks a lot for listening. Thanks for having us here to talk about tall buildings.
Perhaps you have to travel.
Oh, right. Samantha has to catch a flight. Thanks.
So, if you have one quick question, if not, we can.
I have a question related to your section or your part talking about nature, because I really get interested into this idea of biomimicry, which is getting inspired by nature. And I work on these on my early project or research a bit, and I want to know how you approach the, how could I say that, the scale problem. Well, let's not call it a problem, let's more call it a challenge, but about like, you've been talking about bamboo and the structure of bamboo, but bamboo is really, it couldn't obviously not go like to 100 meters, so you'll have to sort of, what's your approach with this?
Be fearless of scale is kind of the first point. Scale is just, it's almost imaginary. You can do whatever you want with scale, and use the principles, the fundamental principles, as your driver rather than the fear of something that's huge, right? Because the projects that I showed you, they're not all built, but a lot of them were built. The scale's like, if you start to think about it too much, you get too nervous and you stop, right? Because it's too nerve-wracking. Okay, but imagine the principle of the wall of the bamboo, right? Just as an idea, and the wall is made up of a series of columns. Just as an idea that you compress or you put in tension. And what you want to do is you want to create diaphragms within that wall that protect those columns. As an idea. It could be a concrete wall on the outside, right? It could be something that you put all the material that you possibly can on the outside, and you link it with these diaphragms. And you can translate that. It can be so small scale, it could be a piece of art, or it could be a building that's 150 stories tall. It's the same exact principle. You have to calculate the forces after you have the concept, and you have to apply the material. Is it steel or is it concrete, right? But if you want to go super tall, the idea of the form with the structure being as far out as possible is really important. And maybe you hollow the inside out. If you want to go super tall, you don't have use of that inside space so much. And I think what Rosa studied and developed with the Bionic Tower is that there are hollow areas within, right? That you don't get daylight. You can't get daylight deep into the space. People are, it's like being in a basement, right? But the material's on the outside. So what we're thinking about is the material being far out. It could be like bamboo, but maybe the occupied space is beyond. Maybe it's not hitting the ground. Maybe it's cantilevered off of the bamboo membrane. And so all of a sudden you start thinking, all this stuff is related, but it could be at huge scales. And you go super, super tall based on the diameter and what you do inside and outside. So that's kind of the way we think of it. And then you have to verify it over and over and over again to be sure you're right. But that's kind of the way we think about scale. Yeah.
I agree to you of all this explanation, because you start with a straight line and you arrive to a curved line.
Straight line versus a curved line.
Straight line is a normal frame.
Yeah.
Curved line is a bunch of frame. That's what we talk. We are talking of the same.
Yeah.
Only you have to separate more the points of the side. And you arrive where
Yeah. Yeah.
you are right.
That's true. Yeah, and what you do within those forms is really important, how you resolve them, because there's an architecture to it too that has to work, right? So that's where I think the art is that we're not just trying to make something that we possibly could build, but how do you use it, right?
The next step will be how to prefabricate it, but you don't want to prefabricate it.
No, I think that's a good idea.
He has a prefabricator. Don't make
Okay.
a conversation between. There is another question or commentary.
What about the backbone of bamboo in compression? Natural bamboo doesn't work
Yeah, it's because
with compression.
no, it does. Well, the walls take compression, of course, they have to, under their own weight, but also this, right? So it's the magic, I'll say the magic of the diaphragm placement. If the diaphragms are very, very close together, the wall thickness doesn't have to be that great, and you can have great resistance. Yeah. So it's that relationship. So it's the principles of unbraced length and material associated with that unbraced length that you have to evaluate. And what's tricky with what we do is that you can't put diaphragms everywhere because you got to have people there, and you have to have the economy of structure. So how do you space that out so that you prevent buckling, but maybe you have to make the members of walls thicker because you can't get the diaphragm close enough. So these are problems that we have. Like, those are real problems that gets down into the actual engineering of the components.
I would like to ask you about something that I think you didn't talk about much, is like horizontal structure. In the example you showed of one of the lessons you showed about San Francisco, it was like a building of apartments where you only had like the core.
Yep.
And I guess it was like a flat slab.
Yep.
Like how to deal with that, because here in Spain, like the problem of seismicity is not that big in general,
Yep.
and that's the way we build. Like we tend to do flat slab or water slab, but without hanging beams.
Mhm.
So I would like to ask you about how's the connection between flat slab and higher build.
Yeah. So we do a couple of things, and this is related to shear mostly, but the thinner you make that slab, the more important shear is that the interface between the column and the slab. So we have shear bands and shear studded rails that we use to strengthen that joint. And also we run the rebar through the joints so we create some continuity through the longitudinal reinforcement. And the reason why the slabs are thin is because you're trying to save material, right?
Yeah.
And usually the reason why they're thin is because you post-tension them. Because if you don't do that, you'll have deflection problems, especially for long spans with thin slabs. So what's really interesting is that you could then use the cables running through the joint or right next to the column to also create better resiliency. But you have to look at the displacement, floor-to-floor displacement of the slab and the column to be sure that during an earthquake, when it translates, you don't have some kind of a mechanism that gets created there. So all of those pieces add up into the design of that joint. But what's really important, actually, that you hit on is something I didn't show here, but is how to deal with the slab. Yeah. So one of the things that we've discovered is that post-tensioning, of course, is really a benefit. But we've been post-tensioning slabs in a linear way. Like I have a column here and I have a column there. I drape the cables, right? Usually I drape it through the depth of the slab. What we're finding though is that the force flows are actually not straight. They're actually more like the tower bulbous shape that I showed you. That's where the forces are going. They're actually moving in a more fluid way. So what we've done is we've mapped the post-tensioning from point to point, and what appears is these forms that in some ways looks like this, where the cables are then placed change in elevation, but also change in plan. So you get this combined effect. And we're finding that that's more efficient. So the cable layout for the PT slab looks like a flower. It looks like a flower. And you might have some straight cables, but a lot of them are curved. Not hugely curved, right? But nominally curved, and it's a more efficient way to design it. And it comes from these optimization studies that we've used for tall buildings that I showed you. But load the slab and plan, and you'll actually find that the force flows are not point to point. So we think that that's the next step for slabs, seismic issues, but also gravity issues to try to make them even more efficient. So we believe that's kind of the next big thing for post-tension slabs.
Yeah, because in the end, most of the material is not used in columns, it's used on slabs.
Right.
So
Exactly. There's a ton of material in the slab.
It's clear.
that's
Right. So the idea of taking away material where you don't need it, if you can, convince somebody to do that, good idea. Varying the cable layout in a smart way, don't just connect it point to point. Bands don't even work that well. It's better if you actually look at it more fluidly. That also helps. Think about how many slabs we build. We have slabs in every single building almost, right?
One slab here.
Huh?
They arrive higher, you don't have slabs. Almost the same.
Yeah, no, it's true.
Only minimum.
Someone? Okay, then we close the session. We greet Mark and we thank you very much. You have had a very good and very interesting presentation.
Thank you.
And very good collaboration with us. And I greet